It's all about risk. I think there's becoming an increased realization that in order to attain a clean energy system, you have to do something more than wind and solar, and nuclear is a very viable solution. And I think as we proceed through these projects, the risk aspects will decrease and their willingness to move forward will increase.
This is EnergyCast, and I'm Jay Downhauer. Today we are talking about small modular reactors, the little solution that may be the path forward for nuclear energy. You've heard me talk about SMRs going all the way back to episode 16. Now, as we close in on our 100th episode, I had a chance to talk to the world's industry leader on the technology and the path forward for commercialization. As the name suggests, small modular reactors are self-contained nuclear reactors, typically a fraction of the reactor sizes we've been seeing for decades. The two AP1000 units being installed at Southern Company's Vogtle plant are 1,000 megawatts of power. Each of my guess reactors are capable of 77, but you can combine them into a single building and get the power comparable to a typical power plant. My guest is currently planning on a 12-pack configuration as the most common design. The modular aspect makes construction much easier. Nuclear plants today have to have their giant reactors built on site. My guest says their reactors would be built in a controlled environment at a dedicated facility. He says this will streamline construction so that the unique building can be structured on site while the reactors are built at the factory. Like all Gen 4 nuclear technology is being developed today, it's critical that this technology is walk-away safe to avoid situations like Fukushima, where a tsunami made operations impossible and knocked out all the ancillary power. If that had happened in this case, the modules would sit patiently in their containment, no danger of a meltdown. It's these benefits that have made small modular reactors the biggest thing in nuclear right now. My guest today is Dom Claudio, Director of Sales for NuScale Power, an SMR developer based in Oregon. Dom is based here in Charlotte, and I would have loved to talk to him in person, but that would have been difficult for the format we were doing. You see, this interview was part of my segment for the North American Young Generation in Nuclear virtual conference I hosted last month. You may remember my live episode from episode 65. This is the second year participating with NAYGN. I got to host two events. The second will be covered in episode 100. It was an exciting time to be talking to NuScale. In late August, they finally received their design approval from the U.S. Nuclear Regulatory Commission. This is essentially what grants permission for them to go out and build a plant. It was a first for a small modular reactor design in history and a watershed moment for nuclear power. This appearance was one of the first times since the announcement that NuScale had spoken to the public. We led off this panel with a short PowerPoint from Dom, which is linked here in the show notes. I also took questions from the audience, which was nice because the attendees all know more about this subject matter than me. I hope you enjoy my conversation with Dom Claudio. Here we are again. Today should be exciting as well and very newsworthy. We've got NuScale Power. As I was saying yesterday, I think it's a very exciting time for the nuclear industry as a whole. You got Vogtle 3 and 4. You got a lot of Gen 4 coming online, a lot of dollars being thrown around. And I think that we are now in a very interesting era where we're going to see a lot of developments happening with SMRs. Our guest today is going to take us through all of that and show us exactly how soon we might be ramping up on that. Now, my big exposure to SMRs was through the Office of Nuclear Energy. About a year and a half ago, I was approached by that group. I couldn't believe it. The podcast was still pretty new at the time. Ed McGinnis, who's high up there at the Office of Nuclear Energy, and the big thing that they were pushing was was SMRs. Now, we talked about a lot of things with nuclear energy. We ran the gamut, and Ed was a terrific guest, but SMRs was really the bread and butter. That was the thing they wanted to talk about, and I think that's what DOE is really excited about right now, in addition to all the other things that they're working on. So with that, I will take us right into our guest. It's Dom Claudio, Director of Sales for NuScale Power. And Dom, how are you? Can you still hear me after all that preamble?
I'm doing well, and I can hear you fine.
All right, fantastic.
But first, let me say thank you, Jay, for the opportunity to speak here today and to present to NAYGN. I think that's a very important group. Certainly, that is the future as far as sustainable nuclear energy is concerned. It's a people-oriented business. It doesn't happen without the folks that are on this call. So I appreciate the opportunity to speak about NuScale today to this particular group, and just want to express my appreciation. So thank you for that. So with that said, let's start speaking about a little bit of a global reality. As we sit here today, 1.1 billion people still live without any access to electricity. And that's a pretty significant number when you look at quality of life and economic impact. So there's definitely a need for additional electricity. Along those same lines, half of the world's population is living under a water stress situation. Again, as we talk about applications that require a lot of energy, desalination is one of them, and this would be a solution for that issue. What we know is that over 1 billion metric tons of food is lost to waste each year due to lack of cooling. Again, when you think about refrigeration, you think about load demand, you think about diversification of energy sources. This is a big issue as, again, we look at quality of life and what could be possible from the standpoint of spreading economic benefit more globally. And then finally, the elephant in the room from the standpoint that not only are we dealing with particulate pollution, if you will, from a air pollution point of view, but CO2 and global warming is a big issue to the extent that not only is electricity required globally, but the move toward carbon-free electricity and the move away from fossil generation is also a significant driver globally. And we've all heard about the Paris Accords, the Kyoto Protocols from several years ago, and a continuing drive to minimize the carbon generation and move away from fossil. And that sort of sets the table a little bit, and a little bit about NuScale. So NuScale was formed in 2007 for the sole purpose of completing and designing and commercializing a small modular reactor. And at the core, we'll talk about the NuScale Power Module, which is the core of the technology. But that was the purpose of why the company was formed and established. The initial concept, though, even goes back even further from the standpoint that it was developed and tested as far back as the year 2000 with the U.S. DOE as part of a multi-application small light water reactor program. And this had a lot to do with the passive safety case that's found in the AP600 and the AP1000. So what's noteworthy about this is that the technology from which NuScale is built, not only does it use a very common fuel from a PWR standpoint, it uses water as its coolant, but the safety case and the basis of the safety case as it relates to natural circulation is also very well grounded. There is a lot of data that supports that and a lot of experience, which is what the NRC looks for when it evaluates the technology. At the heart of the NuScale small modular reactor technology is the NuScale Power Module. And what makes this unique is that it includes a reactor vessel, the steam generators, the pressurizer, and the containment vessel all in one integral package. And that package can be factory built, which is very important as we look at some of the risk and the cost involved in building a nuclear power plant. By being able to build essentially the core of the NSSS system in a factory, while at the same time being able to build the civil works, if you will, at site, allows one to cut the schedule in half, basically, as opposed to building the civil structures and the NSSS system in series. That's an important factor from a scheduling standpoint, helps us control the cost, helps us control the quality. Also, because of the simple design, we've eliminated our reactor coolant pumps, large bore piping, and other systems and components that are found in conventional gigawatt-sized plants, and the safety systems that are associated with them. So not only from a capital expenditure point of view are those costs not incurred, but also from an operational point of view, because those external components just simply don't exist. So each module is capable of producing 200 megawatts thermal with its own dedicated power conversion system. It's able to produce 60 megawatts electric. And our base model, if you will, our reference plant, that which we have submitted to the NRC and have had approved, essentially is a 12-module design capable of producing 720 megawatts of electricity gross. And that's, again, a preliminary design, if you will. So we just talked about the NuScale power module. That goes into a reactor building, buildings below grade, seismically qualified to a 0.5 G, aircraft resistant. The module is nearly totally submerged in a pool of water, which is essentially the ultimate heat sink. In the event of an event, in this case, the ultimate heat sink is sitting there, and we can demonstrate that it's walkaway safe from the standpoint that there is no AC or DC power required, no operator action required, and no external water required. That reactor building sits in the middle of essentially a 35-acre plot, which is in the bottom right. On either side of that reactor building are 2 turbine generator buildings. Each turbine generator building houses 6 turbine generators. And again, that's our base design, if you will. So what can the NuScale plant do? It can provide power for desalination operation, hydrogen production, support oil refineries, support mission-critical facilities. We can provide high levels of reliability, 4 nines or more, to a mission-critical facility, which may be a hospital, which may be a data center, which may be a Department of Defense location. Those that require very high levels of reliability can count on this design and providing them that. And then obviously wind and solar are complementary technologies. Nuclear, wind, solar, hydro, they're all part of the solution. And to the extent that these technologies can integrate, all the better. We ran a test that this is a unique feature of the NuScale design. The NuScale output could complement what is found in the wind farm. That responsiveness is, again, very unique, and it's something that, to the extent that the NuScale power module can make the case of complementing what's already in place from a renewable point of view, this is the basis of that argument. There is an economic case to be made as you progress with renewables, wind and solar, beyond certain levels, if reliability is a key component of what you're trying to provide your customer base as a utility. As you get higher and higher in renewables, the redundancy and the capacity factor drive the amount of renewable capacity that you need to build. Once you get above a certain level, the economics start flipping away from renewables. You need nuclear at the end of the day in order to have that reliability. A little bit about international opportunities. We're doing work up in Canada. We've been involved in the UK. We have an MOU, Nuclear Electrica in Romania, as well as Czech Republic, Jordan, and a number of other international opportunities in Europe, the Middle East, Southeast Asia, and Africa. And then finally, a celebratory note, we were able to make history here in August by becoming the first ever small modular reactor to receive the design approval from the U.S. Nuclear Regulatory Commission. So with that said, Jay, I'm happy to answer any questions or dive into any of the topics that I mentioned a little bit more deeply if you'd like.
I think that really explains a lot. On August 28th, you finally got your design approval from the NRC. You're the first SMR to do so. And I know that this has been a crazy year with 2020. You haven't been able to speak very much in public. A virtual conference, I think, is good as any. We're all really excited for you. And so what I'd like to do is we're going to just do this once. I want everybody here to show NuScale how we feel about them. Go ahead, light up the microphones, light up the cameras. If we crash the system, we'll just log back in. Everybody get on real quick and let's show them a round of applause. Let's start seeing those cameras. Keep it going, girl. Let's light up those cameras if you're decent.
On behalf of folks who worked on this project, getting to this point, I'm happy to take a bow on behalf of NuScale. Thank you so much.
You bet. Thank you so much. And thank you, Tyler, for setting that up. We didn't get very many cameras. People really must be in their underwear. I don't know. Let me go ahead and do the first question. How many days did it take? And give us a rundown. How many days, how many man hours, how many reams of legal paper did it take to get that design approval?
I think days may not be the appropriate unit of measure, but I will give you some stats on that. So the design certification application was over 12,000 pages. It included over 14 topical reports. It required 2 million labor man-hours. It included 800 people. It included over 50 suppliers and partners, and it cost over $500 million, $500 million. And that was the application. Once the application was submitted to the NRC, they reviewed it for about 3.5 years, and the NRC itself consumed over 250,000 man-hours in its review process. So it's a daunting task. It really is.
That's the recipe for doing it. The first question is, I'm just going to do as many of these questions as I can. Chris has, will the plants be licensed under 10 CFR 50 or 52?
This would be under Part 52.
Okay. Going on to some of my questions, what is the current plan for commercialization in the United States? And I want to talk about the two phases. What's the plan for the first plant, and then what's the plan for the second plant, and how fast do you see it being proliferated? I don't know if that's the right word, but moving commercially.
So our first customer is UAMPS, the Utah Associated Municipal Power Systems, and they are working on what's called the Carbon-Free Power Project, which is located at Idaho National Labs. We have a contract with them to support the construction and deployment of a NuScale SMR, and their schedule is they would like the first module to have a commercial operation date of 2029. And so we're supporting that. To the extent that that project represents, I think, a realization of commercialization, it's a very important project. The Department of Energy also views it as an important project. They are in the process of contributing $1.355 billion in addressing the potential for first-of-a-kind risks. So that's working as a de-risking fund, if you will. That's the process, and that's the schedule that we're supporting UAMPS. From a supply chain standpoint, from a NuScale standpoint, we can support a quicker deployment. And we are in conversations now, again, covered by NDAs, in which we're evaluating deployments as early as 27. As far as how those projects get sequenced, how we deal with first-of-a-kind issue, how multiple buyers can benefit from each other's experiences, that's in the works, that's being worked on. But there's certainly a lot of interest as you look at the legislative landscape, state-by-state basis. Many states have already put in very aggressive carbon targets that are being imposed on the power companies in those areas. I can think of one state that by the end of 2021, next year, they need to submit a plan to the state legislation of how they're going to meet their carbon targets in a reliable fashion. A lot of drivers, a lot of interest, and a lot of concern, frankly, on how to get there in a carbon-free manner, but also understanding that nuclear has to be a part of it and that this is a very real challenge that needs to be addressed.
Going to a question from Gaston, it's a technical question. What is the estimated fuel cycle for one of the power units, and what is the expected lifetime of each power unit?
So each module has 37 fuel assemblies. They're PWR, light water reactor fuels are made by Framatome, very common configuration. In fact, it's almost the exact same configuration that you would find in a large PWR, except at half height. The fuel plan is that at each outage, and each outage would be on a 24-month cycle, you would replace a third of the core. It's about a 10-day outage. The other 11 modules can operate. You're just losing 1/12 of your output during that period of time. And actually, the long pole in that 10 from a scheduling standpoint is not the refueling so much as it is the ISI, the in-service inspection of the welds and things of that nature. That's the fuel approach.
Glenn asked, and this may be early days, but what is the cost of a 12-pack, that's a 12 by 60 megawatt site? Compared to the AP1000, we will need 3 12-packs. And look, I think that every nuclear plant has an estimate when they first start, right? I'll give you a little bit of forgiveness there, but what are you thinking about costs, installed costs?
Just to speak about the NuScale cost, the first plant target from an LCOE standpoint, the UAMPS is $65 per megawatt hour. And that cost has been developed in conjunction with our partner and owner, Fluor, who has provided an AACE International Class 4 estimate that has over 14,000 line items. As far as the power modules themselves, that estimate for construction is at a Class 3 estimate. We feel that we have a fairly high level of confidence in our ability to come in at the estimates, in particular because we have Fluor really leading the charge from an estimating standpoint as an EPC. We found that that's a much better model than having the vendor OEM lead the project and come up with the estimates.
And it sounds to me like the 12-pack is really what you're thinking your design's going to be. I recently interviewed X Energy. One of their guys is actually here in Charlotte, like us, Darren Gale, and they've got 80 megawatt modules. I think they were going to do 4 of them for a 320 megawatt facility. Is that what you're thinking about, sticking with that 720? Would you have multiple 720s at a single site? What are you thinking about the distribution there?
Looking at the 12 module configuration and 12 bay building, it is scalable. In fact, I was having a conversation with someone today who's interested in starting out with 6 modules, having 360 or so megawatts of capacity available to them, and then his anticipated load growth to then fill in the additional bays. And the incremental cost to grow, get that second 360 as an example, is really fairly low. From his view, the capital cost may be a little higher if you're only using 6 of the 12 bays. Your operational cost is lower, And depending on where you are and what your needs may be, that would be a very useful configuration. We are looking at that configuration, putting 6 modules in a 12-bay building. And there are also other opportunities with small island nations, let's say, or those who may have a grid that may not be able to accommodate 720 megawatts, building a 6-bay building, if you will, as opposed to a 12-bay building, and putting 6 modules in that is also a reasonable approach, and something that, again, builds on the acceptance of the technology by the NRC because you're using the same modules.
Dom, you're director of sales. You're dealing with utilities here in the United States. What is the appetite from utilities at this point? What do they want to see from NuScale before they sign on the dotted line for commercial scale facility?
Good question. It's all about risk. I think there's becoming an increased realization on the part of U.S. utilities specifically that in order to attain a clean energy system, you have to do something more than wind and solar and nuclear is a very viable solution. However, in all honesty, it's been marred by recent poor project execution. And so to the extent that that becomes a question, that's certainly one of the ones that I have to answer most frequently. With our association with Fluor, having a project at UAMPS, having some hopefully additional near-term deployments, we should be able to not only address the risk as it's associated from a regulatory process when you look at the COLA, but also address the risk from a project execution standpoint when it comes to cost and schedule and constructing a plan. Success begets success, if you will. And I think as we proceed through these projects and are able to show what we've learned and what we're capable of, the risk aspect to the buyers will decrease and their willingness to move forward will increase.
Amanda Smith asks, how many people to support daily operations? I assume commercially.
The standalone plant, you're looking at about 305 people from an operations point of view. However, we're approaching this a little bit differently in looking at a fleet of NuScale plants as a fleet and to be able to utilize shared services. So let's take refueling as an example. In one scenario, you can have staff at your plant totally dedicated to refueling. Every other month or so, you could be refueling, or you can refuel a whole bunch in the spring and the fall and not have to refuel for several months in between. Another approach is that a number of NuScale owners could share those services. And rather than each of them having a refueling staff or a maintenance staff or you name it, those services are shared and would rotate among the plants. We're getting to the point where we believe we can get that number from 305 down to 270 years.
Ben B, he had a lot of likes on his question, and you talked about this idea of you load following. This was a feature that I wasn't aware that SMRs could do to this extent, but Ben's question is, will NuScale's SMR have similar ramp rates as conventional peaking units in order to complement the intermittent variable nature of renewables? How does it compare with conventional peakers?
It's much more comparable to a conventional gas peaker than it is a gigawatt-sized plant. How I would reference that is to keep in mind that turbine generator that we're considering, commercial-grade turbine generator, I don't have the ramp rates at my fingertips, but I can provide those. It all depends on the turbine generator, and we can do a fairly considerable steam bypass without tripping the reactor, which is really the governing sequence and ramp rate, if you will, to allow the nuclear output, the NuScale output, to match what is required, say, from wind, as I had shown earlier.
Okay, so we've talked about utilities, and you talked at the end of your presentation about all these other countries, and I thought it was interesting that there was only one Scandinavian country, Finland. It seems like they would be all over this, but maybe you can speak to that in just a second. But you're pursuing licenses and agreements from what's been publicly released. Canada, Czech Republic, Jordan, Romania. How do those plans fit in with your time? And you talked about you can run and chew gum at the same time. How do you see those facilities maybe going online compared with the domestic ones?
They each have their own schedule, their own drivers. It seems to me that sometimes even the drivers are not predictable from the standpoint of how they impact the schedule. At this point, I see them being in sequence. I see them post-2030, but things may change and they may desire to have a NuScale facility earlier. But I would say each of those is probably post-2030.
Yeah. One of the things we discussed on a pre-call was long-term fuel deals. And this has got a lot of geopolitical ramifications to it. How important is that? And what is the global competition like for those kinds of deals? They're essentially locked in once they're using your product, right?
Not necessarily. So we have an arrangement with Framatome to provide the initial fuel loads. It was important to have that in place just with our regulatory process, and it helps the customer have fuel in his plant to start start with and know that that fuel's been qualified. However, what's also true is that this is fairly common fuel. It's PWR fuel, and I may not say it's a commodity, but it's tending toward that direction. So to the extent that an owner wishes at some point in time, past the initial fuel loads, to change fuel vendors, there's a process in place to do that, to qualify the fuel. That changes in the existing fleet even now among the installed base. The buyer is free to proceed with any fuel company or any fuel vendor that he wishes. At this point, we're providing the fuel that's been qualified, and I suppose if there was really a hard stop there, that could be addressed as well. But by no means is the buyer restricted to the initial fuel vendor throughout the life of the plant.
Jeremy Miller, he's actually going to be a moderator on a VC Summer panel tomorrow. What is the life of the module plant? Legacy plants have 40-year initial license and are pursuing extension for 20, 40 years in some cases. Is the initial plant life going to be 40 or 60? We're just going to go directly to 60?
Right now, from a licensing standpoint, licensing for 40 is well established. However, we strongly believe that at some point in the future, going through a life extension process, as we've seen among the installed base, from 40 to 60, is very doable. The modules themselves are qualified to 60, and the building is qualified to 100 years. To the extent that, let's say you even wanted to go past 60, you wouldn't have to rebuild the plant. All you'd have to do is replace a module, which is a fairly inexpensive way to get those incremental years beyond the initial licensing time.
Tyler asks, with UAMs or other NuScale projects, what do you expect as far as how many staff will be NuScale versus the utility employees as you go through construction and approach plant operations? What's going to be the split, you think?
That's a good question. From a total staff point of view, during construction, we're looking at about 1,100 people. It doesn't include manufacturing. And of that 1,100, I would say 25 to 35% might be NuScale office people helping with the design.
Matthew asks, can you add any more details on oncoming work with developing countries, as well as broader nuclear advocacy? And that's something I talk about a lot, is developing countries and where does this fit in for them? Probably the following phase, right?
Yeah, we're active in Africa. We're active in Southeast Asia. When you look at some of the developing countries, and we spoke about food shortages and water requirements and just not having electricity, especially speaking of the African nations, they are very rich in mining material. However, it takes reliable power to not only bring those resources to the surface, but it also takes a lot of reliability, especially when you're digging a hole well into the ground, to have the ventilation and to be able to rely on that ventilation and the power to support that ventilation. They are actually developing programs. They have staffs that are focused on nuclear energy, on SMRs, and we're engaging with them as often as we can.
There's a lot of interest in Eastern Europe, Czech Republic, Romania. What about the construction resources in those countries? And do you think that'll be a challenge during construction? Are there a lot of, for instance, nuclear-grade welders in Eastern Europe?
Yeah. Interestingly enough, what I found was that there are actually a fair number of operating plants in Eastern Europe, and those operating plants do have service providers that include qualified welders. I think the backstop to all of that is the utilization of a good EPC, whether it be a Fluor or someone of that nature, who has a global reach and can bring resources almost to anywhere that's required. What I learned is that it's not that big of a question, not that big of an issue, and certainly something that can be addressed and should not be a critical path issue.
Giovanni asks, what does the risk of operating a commercial 12-pack compare to operating a traditional PWR?
From a core damage frequency standpoint, we're 5 orders of magnitude safer than a gigawatt plant. That has to do a lot with the passive design, the fact that the ultimate heat sink is inside the building, and in the event that an event were to occur, you needed to shut down, you would need no external power, you would need no external water, and you would need no operator action. The plant would literally cool itself down, and it would stay in a safe state indefinitely.
Just for the record, a 12-pack, you can cogen at the same location, right?
You mean as far as having different applications?
Yes.
Yeah, if you wanted to commit some of the modules to electricity generation and some others, say, to steam generation, that could be accommodated.
Hey, this is John. Once burnt is spent fuel handling, storage, and processing similar to current processes used for PWRs. What is that like?
Yeah, it is. It follows the DOE standards as far as spent fuel or used fuel. Utilities that may already have nuclear power plants, you would handle the spent fuel exactly the same.
One of the things we also discussed, this is going international, the SMR is designed for 60 hertz. Is that a challenge?
Not terribly. We're using commercial-grade turbine generators, and to the extent that you would install a turbine generator that would produce 50 hertz versus 60 hertz, obviously there would be changes that would need to be done in the BOP, the balance of plant, but it's not anything that is especially challenging. It is a bit of a change, but should not affect the safety case from a regulatory process, would have minimal impact.
Stephen, does implementing the dry cooling system cause less power output?
Dry cooling relative to wet cooling is a little less efficient. I'm not sure how that would translate from a power output point of view, but I would agree that just dry cooling relative to wet cooling is a less efficient way to go. However, I will say this, if you look at water availability, if you look at the cost of water in order to have sustainable water, that delta actually is shrinking very fast. Even in places where you would imagine that water was plentiful, in places like Virginia, as an example, 2 new gas plants went up recently, and both of those in relatively lush areas are using dry cooling versus wet cooling. I think what's driving that decision is water conservation. The choice we provide is obviously up to the owner whether they want to go wet or dry, but we are also providing dry as an alternative.
You know, given the design approval news, Dom, I want to get into your funding. And I'd have to think that you might be getting a lot more private now that you've gotten over that massive hurdle.
Absolutely. To the extent that investors wish to see a return within a predictable amount of time, to the extent that going through a regulatory licensing process has risk associated with it from a scheduling point of view, and the fact that that's behind us now is one risk element that is taken off the table when dealing with an investor. If this was a year ago, we'd be saying, yep, we'll have our license in a year. And they say, okay, that's wonderful. It's very different than saying we have achieved our approval, and that elevates the level of confidence of the investors. I would say yes, just generally speaking, the phone's ringing more, and there is increased interest, not only as a result of having achieved this regulatory milestone, but also moving forward with the UAMPS project. That's another de-risking activity. Those two elements are expected to increase the amount of dialogue we're having with investors and hopefully translates into funding.
Yeah, I'll do one more question from the audience here. Thank you so much for your questions, everybody. Dom's been really knocking out these questions fast. I would have run out of my questions a long time ago, but Keith asks, what is the effect on tech specs compared to a normal LWR? Do you have fewer systems to worry about from an operational standpoint, or is that similar to now?
Going back to, if you recall, the slide that I showed that had the NuScale power module, it was a self-contained, didn't have pumps, didn't have large bore piping, didn't have a lot of things that you would find in a typical gigawatt plant. Those are systems that simply don't exist and don't require maintenance groups in order to provide preventive maintenance on them and all those things. The volume of work and the number of people required to run our plant is markedly less than you would find in a typical gigawatt PWR.
We're getting to the end of the program here. We have several folks here listening today who've been watching NuScale for a long time. So what job opportunities do you have now, and what should folks be focusing on academic-wise to align themselves for a career in the SMR space? And I'll also add to this before Dom answers, I had Dom's colleague, Scott Rasmussen, for a panel at UNC earlier this year, seemed like a lifetime ago, and I think they went through all of his business cards by the end of it. So give the plug for NuScale. What opportunities do you have there, Dom?
So as you would imagine, a lot of technical positions, engineering, licensing, within engineering, thermohydraulics, robotics, INC, civil structural, design analysis, nuclear, manufacturing. What's interesting is whether it be where we are now in the design process or the construction process or even the operations process, the number of nuclear engineers that you need is not as many as you think. There are a lot of mechanical engineers. One of the market segments that we're focusing on is coal replacements. And if you take a typical coal plant, you're making steam utilizing coal, but that steam goes into the balance of plant, in which you turn that steam into electricity. Well, that balance of plant looks very similar to what you would find in a NuScale plant. So to the extent that you have engineers and you have technicians and folks of that nature working in a BOP fossil plant, those same jobs are applicable in our plant. And it's actually a very important statement that we make when we talk to utilities who are looking to replace coal plants, are concerned about the job loss, and are heartened by the fact that many of the jobs that would otherwise be lost at that coal plant would be applicable in our plant. That seems like maybe a good way to put a box around that.
All right. Dom Claudio, NuScale Power, thank you so much for your time. And hey, everybody give a virtual round of applause there for Mr. Claudio there. Fantastic work. And hey, everybody, thank you so much for your questions. They were really, really great. And I hope everyone enjoys the rest of their virtual conference. It's been a real pleasure. Thank you so much. That was Dom Claudio, Director of Sales for NuScale Power, a small modular reactor developer based in Oregon. And since the time of this recording, NuScale announced they could achieve a 25% increase in each power module, so the new rating per module is 77 megawatts electric. I want to thank Dom for his time, as well as Scott Rasmussen and Diane Hughes at NuScale for setting this up, and Tyler Andrews at the Carolina chapter of NAYGN for letting me host this event. You can find plenty of pictures on energy-cast.com, as well as on Instagram and Parler at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 99. Be sure to join us next week, our 100th episode, when we talk to the world's leading fusion experts. Until then, I'm Jay Dowenhauer. We'll see you next time.